say chapter 5 sounds right, I think, maybe. We're going to talk about nomenclature here in this chapter. We're going to talk about how to name pretty much everything. And we're going to cover how to name ionic compounds, covalent compounds, acids as well. So let's get into it. First off, though, when we talk about sort of naming, especially with ionic compounds, just a reminder that when we do look at the periodic table, there are certain elements that will form really fixed charges, which is really important when we do nomenclature. And everybody in group number 1 on the periodic table will form a +1 charge. Everybody there in group 2 will form a +2 charge. Skipping our transition metal region, and then we have 3, 4, 5, 6, and 7, and 8 down this way. So over to group 3, and really in most cases, again, it's aluminum here that we see the most, which is going to be +3 for aluminum. Actually, I'll put +3 over here. Then if you remember, we do have on the periodic table sort of that staircase that kind of comes down through this region here. And above the staircase are nonmetals. There are ones that make fixed charges as well. Group 5 -3, group 6 -2, and group 1, group 7 -1 there. And again, those are the nonmetals above the staircase. A reminder that kind of in those groups there, below the staircase, you have metals actually, and you got some obviously semi-metals on the staircase. But again, we're talking about the nonmetals above. So it's kind of +1, +2, +3 to aluminum there. We kind of skip and then kind of go backwards, -3, -2, -1. Obviously, our metals there, which are group 1, 2, and 3, will form a positive charge, as we talked about. They are typically the ones that will lose electrons, and our nonmetals are typically the ones that will gain electrons and become negatively charged, which is what we see going on there. Our transition metal region here, they can have a variable type of charge, and that does affect the way we name compounds that do contain transition metals versus ones that contain representative type metals. But there are 3 of them there in the transition metal region that also have a fixed charge, and that is our friend there, zinc and cadmium. Oops, cadmium. They will have a +2 charge in terms of when they make a charge. And if you hang a left there at cadmium to silver, silver will do a +1 charge. So those 3, zinc, cadmium, CD, and silver will have a fixed charge, although they are a transition metal. So all the other transition metals through the rest of the periodic table in that region, so everybody else pretty much here, and also again below the staircase to the right of the transition metals, where we got things like tin and lead and those type of elements, they also can have a variable type of charge. Again, even though they're not transition metals, they can make different types of charges. Also a reminder that, again, none of these things have charges unless they really hook up with each other. So metals and nonmetals have to come together for them to gain charges. If you have just sodium metal by itself, it has no charge, or copper metal by itself, it has no charge. Again, they really only get charges as metals and nonmetals come together, as we talked about with bonding, to form ionic compounds, and we get that transfer of electrons that occur in that particular case. Any questions on that there? I think we looked at it, but just in case we didn't, no, we did. All right, let's talk about some common name exceptions to nomenclature. And there are certain things that we do really refer to by its common names, and you should as well. Probably the 2 major ones are these 3 here, are these 2 here, really. Water is H2O. So it is water. If you see H2O, it's dihydrogen monoxide, because nobody wants a refreshing glass of dihydrogen monoxide, right? So they would rather have a glass of water. So make sure you just put water when you see H2O and move on with your life. It's not a trick question or anything like that. NH3 is ammonia. And And this one should not be confused later on when we talk about a polyatomic ion that looks very similar to it, which is NH4+. But this is obviously no charge, not an ion, it's ammonia. And organic wise here, this is the simplest organic sort of molecule you could have. CH4, which is methane. It's like the stuff that comes out of your gas vent there when you light your Bunsen burner. So definitely if you see these three formulas, you really should just go by the common name, and everybody goes by the common name. So don't use sort of the systematic name of naming these guys. All right, so let's talk a little bit about naming. And when we talk about naming compounds, we have binary compounds. Binary compounds are compounds that contain two elements. And there's really two types of compounds, and they really do follow the same thing that we talked about when we talked about bonding. There's really ionic and molecular or covalent sort of compounds. So compounds that contain a metal and a non-metal are going to form an ionic compound. And as we talked about with bonding, because of those periodic trends, what we're going to see is that electron being transferred from the metal to the non-metal. That's going to result in our metal making a positive ion, which is a cation, and our non-metal making a negative ion when it gains those electrons, which is known as an anion. And as we talked about with bonding, again, in an ionic compound, there's absolutely no sharing of electrons that's happening here. So what's holding that together is really the opposite of their charges there, the positive, negative attraction to one another, the electrostatic attraction. That is different than what we talked about with bonding, where we get two nonmetals. Again, this is going to result in some type of covalent bond, where we do have sharing of electrons. And in this particular case, this is sometimes referred to as a covalent compound or a molecular compound. And unlike an ionic bond, because it is made up of two nonmetals, as we talked about with bonding, what's going to happen is some aspect of sharing is going to happen in that compound. Everybody's going to kind of share electrons. And as we talked about, maybe equal sharing, maybe unequal sharing. But, you know, again, we're going to have some type of sharing that's happening between those two. So one of the really important things when you go to name something is really the first thing that you want to kind of do is identify what type of compound you're dealing with. Are you dealing with an ionic sort of compound? Are you dealing with more of a covalent sort of compound? And that's going to lead you down hopefully the right pathway to the way that you name it. They are different in terms of how we name these things, depending on whether they're ionic or they're really non-ionic. And we'll talk about obviously how to do all that there. When we talk about ionic compounds, which always involve a metal and a non-metal, they are also sometimes broken up into type 1 or type 2 compounds. And we'll talk about, you know, what each of those are in just a second. But they will always contain a positive cation and a negative anion. And it is always the positive guy first, followed by the negative. So you should always do the cation first, followed by the anion. And that goes for both the formula and also the naming. So in both ways, the naming and the formula should always go positive guy followed by negative guy. Also a reminder, as I think we talked about towards the end of one of the chapters, whenever we do put anything that is positive and negative together, the overall charge for the formula does need to equal 0. So again, if we had a sodium ion and an oxide ion here, when we put these together, we would need an extra sodium ion to balance out the charge to get to 0. And that would get us Na2O, again, 2 sodiums and 1 oxygen in this case. Remember that the basis for why when we put something that has opposite charges together in an ionic compound in terms of their formula to get it to 0 is the idea of the bonding aspect of it. As we saw, that allows each of those guys to achieve noble gas configuration, right, and become really stable. So again, without the second sodium in this case, the oxygen would not be able to get over on the periodic table to neon's configuration. It would only be able to gain 1 electron and it would be short, right? So it needs that extra sodium to gain that extra electron so it can gain 2 total electrons and move over when you look on the periodic table again from its positioning by gaining one electron from one sodium, then it gains another electron for another sodium. Again, it's able to get to neons configuration and be really stable. That also allows each sodium to lose one electron, and that would allow each sodium, which is actually after neon, to back up to neons configuration. So again, that is the importance of it. When we put the formula together, again, as you see there, sodium, which is the metal, coming first, followed by oxygen, which is our non-metal, which is our negative ion, coming second. And again, always equals 0. The simplest way possible to get to 0 is the proper formula for ionic compounds. Any questions on that there? Now, what is the difference between type 1 and type 2 compounds? Type 1 and type 2 compounds, once again, are ionic compounds. And it always involves a metal and a non-metal. And as we talked about, we have that transfer of electrons. But in terms of naming, it is always the metal that is the most important. It really determines how you go about naming things. So in any type of naming, if you have a metal involved, it's really the one that you want to look at and figure out, what type of metal you're dealing with. And that is going to basically help you name it correctly. So definitely always a metal. Always look at the metal. It gives you the way that you want to name these things. So what is a type 1 compound? A type 1 compound is when you have a metal, which again is the most important part here. It only can make one type of charge. Basically, it has a fixed positive charge. So those are our guys. Basically, if they are a type 1 compound, you have that metal from group 1, 2, 3 on the periodic table, which is aluminum, or it's zinc, cadmium, or silver. You pretty much hit any of those metals in the compound, it is pretty much a type 1 compound. And the way that we name them is pretty straightforward. We'll talk about that in just a second. Type 2 compounds are, again, the metal is really the most important thing. And in type 2 compounds, the metal falls in the transition metal region, or it's just to the right, again, underneath the staircase where you have things like lead and tin. And the deal with our type 2 compounds is our metal, again, is our transition metals, except for obviously zinc, cadmium, or silver are just to the right, where we got, things like lead, tin, etc. in that area. And the difference here is they can have a variable positive charge. And that is different than type 1, which has a fixed positive charge. So as you can see there, for example, something like chromium could be chromium with a +2 charge. It could be chromium with a +3 charge. Something like copper, in certain cases, copper could be +1 or +2. Something like iron could be +2 or +3. So because it can have a variable charge, you do have to sort of indicate to people what the charge is on the actual metal when we do type 2 naming. Type 1 naming, the metal, because it has a fixed charge, you don't have to worry about telling people something like sodium has a +1 charge, because sodium can only have a +1 charge. So in terms of naming, it's basically known that that's a fixed charge. But in terms of type 2 metals, when they're involved, you do have to kind of let people know, hey, in this case, this is iron with a +2, or this is copper with a +1 in this particular case when we name them. Any questions on either of those different types there? So let's first, though, talk about, kind of each of these things separately from each other, and that is how we go about naming simple cations and anions. And I think we also touched upon it in that chapter as well, but this is a table. And pretty much if it is a cation like we have over here, any of these guys which are positively charged, and we have the ion by itself, we simply use the whole name, really, of the metal for a simple cation. And then we basically just put ion at the end. So as we can see there, Na+ is the sodium ion. We have our Li plus, which is the lithium ion. And obviously you can put ion at the end of all these guys in the table all the way down. Here, we also have H, which is H plus, and we still just use the name of the element, which is the hydrogen ion. Now, hydrogen is a only element that could actually go both ways. It could be positive, but it could also be negative. And all other elements are either positive or negative, but hydrogen really could go either way. It could be positive or negative. And remember, hydrogen really is a nonmetal, but a lot of times it is treated like a metal in terms of naming and so forth, in terms of how we kind of use it, even though it is sort of a nonmetal, obviously. But for our nonmetals here, which make our simple anions, as we talked about, I think in that chapter, we basically use the beginning part of the nonmetal name, but we drop some of the last part and even more of it there, and we insert IDE at the end of it. So here is our fluorine, which becomes fluoride ion. Our chlorine, which becomes a chloride ion. So again, our Cl minus is our chloride ion. Again, our H here would be our hydride ion. So a couple of things about this, as you can see here, if you are to write the formula for an ion, either a cation or an anion by itself, it should always include the charge. Yeah. So if you were asked what is the cation, for example, here for potassium oxide, for example, here. In this case, the cation formula would be K plus. It is not K2 plus, even though there's a 2 there. This 2 means that there are 2 of those potassiums, right? So it's actually 2 of these guys. So if you were asked to write the formula for the cation in this particular ionic compound, you should lay up one of these and not again K2 on the bottom or anything like this. So this is not the correct cation like that, which is a very common thing that people will do. The oxygen there, which is group 6 on the periodic table, its anion would be O2 minus. And again, that would be the formula for the anion. So again, here, when we write the ions by themselves and not together in any type of ionic compound, they should have charges. And again, this is how we name them when they are by themselves. As we talked about previously, again, we need the 2 potassiums so that when we put it together in an ionic compound, the formula itself does not have a charge. So the formula for an ionic compound, which should contain both a metal and a nonmetal together, should not have a charge. You want to put it together, simplest way to get to 0, but it is made up of things that do have charges, which are the individual ions along the way. Any questions on that there? So let's get into some of this. We'll start with type 1 compounds, which again, as I mentioned, are fixed positive charges. And again here, this is our metal and non-metal. And once you see that the metal is a type 1 compound, you pretty much don't need to figure out anything else. So if you can identify and you have the formula given to you, that first off, that's a metal and a non-metal, which means it's ionic. Secondly, the metal is a type 1 metal. That's all you need for the naming part of it. You just pretty much roll with the whole name of the metal. And our non-metal gets the IDE treatment. So as we just saw there, K2O, the first thing that we would want to look at in this situation is that is potassium, which is a metal. That is oxygen, which is a non-metal. So right away, that combination 100% of the time, as we talked about previously, tells us it's ionic. And then it's always, when we have a metal involved, the most important thing, when I look at this metal, that is group 1, which tells me it has a fixed positive charge, and that tells me it's a type 1 compound. And that's pretty much all I need to figure out in this point. Because it's a type 1 metal, I'm going to roll with the whole name there of the metal, which is potassium. And again, the oxygen will drop the last part and get the IDE at the end of it, and it would be oxide. So that it would be potassium oxide in this case. Yes, sir. Oxygen is a -2 from group 6. It has no effect on the name, if that's what you're asking. It has an effect on when you write the formula to make sure that you put it together to equal 0. But in terms of the name, it doesn't have an effect on it. The other thing that doesn't have effect on it, and very common that people want to do because, you know, they think maybe it's more chemistry-like, is they see a 2 here, and all of a sudden they want to use some prefixes like di or something like that along with it. There's absolutely no prefixes used in this situation. You do not use a prefix in an ionic compound ever, pretty much. So you should never, ever do it, even though it's very common people will do that. They'll want to use, like, you know, dipotassium because it says there's a 2. So di seems like what I should use. So there's no prefixes here. You could have 400 potassiums there. It would still just be called potassium. Same thing with the oxygen. You could have like 30 oxygens. It would still be just oxide at the end. So no prefixes or anything like that when you're doing a ionic compound and type 1 or type 2 sort of compound. Other questions on that? Okay. So as we talked about here, and as we see, when we do write that ionic compound in the terms of a formula, should always equal 0, but it does represent something that does have charges. So once again, when we look at something like Ki, when we try to analyze this, once again, that is a metal, that is a non-metal, and again, that tells me it's ionic. Once I know it's ionic and a metal's involved, we're once again going to look at our metal, which is the most important thing, and that is group 1, which tells me it has a fixed positive charge, and also tells me it's a type 1 metal. So at that point, that is how we get to the name of this guy, which is potassium. Again, the whole name of the metal, and the iodine gets the IDE treatment at the end. Once again, the formula itself does not have a overall charge or anything like that, but this potassium iodide is made up of a cation, which would be this formula, and our anion in this case would be I-, which is group 7. And again, +1 - 1 gets us to 0 when we put them together. Any questions on that there? All right, so why don't you try some here, and when we want to give you some names, you write the proper formulas. So let's do magnesium chloride. Let's do a little do some sodium sulfide. Let's do aluminum oxide. All right, so proper names on the left, proper formulas there on the right. See what you come up with here. Okay, let's take a look, see how you're doing. We'll start on the left there. So once again, the first thing you really want to do is identify what you're dealing with. You know, what type of elements are you dealing with? So we do see K, which is a metal. We see Cl, which is a non-metal. So automatically that should be ionic in your head. And again, it's always the metal that's most important here. So we do want to focus in here on our metal. And again, as we talk on a couple of those examples here, potassium is group number 1, which means it has a fixed positive charge. So that tells you that this is a type 1 compound. And again, is that metal that's most important. So once I figure out that this is a type 1 metal, that's all I need really for the naming part of it. We're going to use the whole name of the metal, which is potassium. And again, our non-metal will get the IDE at the end of it. and this would be potassium chloride. Once again, the cation here would be potassium with a +1 charge. Our anion would be Cl, which is group 7, which is a -1 charge. And again, that is why our formula here just needs one of each of them. Any questions on that one there? Same thing here. We take a look. That's zinc, which is a metal. We have sulfur, which is a non-metal. So once again, that tells you it's ionic. The zinc here is actually a type 1 metal, even though it is a transition metal, is one of those 3 exceptions in the transition metal that actually does have a fixed positive charge. The cation is actually zinc with a +2 charge, that's what it always makes. The anion here is sulfur, which is group 6, which is actually a -2 charge. And again, that's why when we put it together, we just need one of each of them for the formula. Here again, really, once we identify zinc as a type 1 compound, that's all we need for the name. It's going to be zinc. And again, our sulfur will get the IDE treatment there at the end of it, which would be sulfide. Any questions on that one there? Rolling here, once again, we got calcium metal, bromine non-metal. Once again, checks the ionic box. Calcium, which is group number 2, has a fixed positive charge, which checks the type 1 box. And that means that's all we need is calcium, whole name of the metal, non-metal, getting the IDE there. So calcium bromide. Once again here, the 2 has no effect on the name. So you do not want to use a prefix or anything like that. This is a calcium, which is group 2, which is a +2 charge. The reason for the 2 again is because Br is group 7 on the periodic table, and that means it has a -1 charge. So the anion here would look like one of these guys, not again Br2 on the bottom with a minus, because that's incorrect. Yeah, so if you had to write the formula for an anion here, it should just be Br-. Any questions on that there? Taking a look at the last one there, we got barium, which is a metal, and we got hydrogen. Again, a reminder, actually is a non-metal. And in this case, barium is group 2, which means it has a fixed positive charge. This is barium that has a +2 charge. This is hydrogen that comes after a metal, and that's pretty much when hydrogen is negative. So if you see hydrogen after a metal in a formula, it's going to be the negative version of it. And again, that is why there's a 2 there, because we do need 2 of them to balance out the charge. And this would then be barium hydride. Yeah. Any questions on that there? Now, speaking of hydrogen, if we had hydrogen in front, say, of another nonmetal, although those are really 2 nonmetals together, hydrogen in this case is really named more like a type 1 compound, a metal. And we think of this as really like H+ and Cl- sort of together. And this would be just hydrogen chloride. So hydrogen is a little unusual in that sense, even though it really is a non-metal. When it gets together with another non-metal, it will be the positive version of it. And the way that we name it is just hydrogen. So we really kind of name it like a type 1 sort of metal, even though it's a non-metal. Even if you had 2 hydrogens, there, for example, like H2S, if this was a gas, that would be basically 2 hydrogens thought of like that, and a sulfide, and this would still be hydrogen sulfide, IDE. So hydrogen is kind of an unusual one when it hooks up with a non-metal, and it's not an acid, which we'll talk about later on. If it's not an acid, it's just kind of there, it's really more named like a type 1 sort of compound, and it's sort of thought of as like a cation like that, even though in reality those guys are sharing electrons, and it's really more of 2 nonmetals together. But in terms of naming, it is sort of named that way. So got hydrogen in front, hydrogen pretty much whatever the negative guy is. We got hydrogen after a metal is going to be the negative version of hydrogen. Any questions on any of those there? Okay, so now to the formulas. When we have the name, again, we just basically want to think about what we got going on. So we got magnesium chloride, so magnesium being a metal, chloride being a non-metal, and that tells us it's ionic, which means we need ions. So we just want the basic ions of each of these things. We know magnesium is group number 2, which means it has a +2 charge. We know chloride is group 7 on the periodic table, which means it has a -1 charge. Now our goal is just to get to 0, and the simplest way to get to 0, we need an extra one of those guys, and we pretty much can just write what we have. I got 1 magnesium. I got 1 and 2 of the chlorides. There you go. Well, MgCl2. Any questions on that there? Coming here, we got sodium, which is a metal. We got sulfide, which is sulfur, which is a non-metal. So once again, this tells me it's ionic. So I want the basic ions that make it up. So the cation for sodium, which is group 1, is +1. Sulfide is group 6 on the periodic table. So that is -2. And once again, here, the simplest way to get to 0 is to get to 2 on each. And that means we need 1 more sodium ion, right? And that tells me I have 1 and 2 sodiums and 1 sulfur, basically. Yeah. And there it is, the proper formula. Lastly, aluminum is group 3 on the periodic table, which has a +3 charge. Oxygen is group 6, which has a -2 charge. In this case here, common number there is 6. You could get that basically just by multiplying 3 by 2, right? And you get 6. So to get aluminum to 6, we need an extra one. And to get oxygen to 6 there, we actually need a couple more. And once again, we could just write what I did there. That is 2 aluminums and 1, 2, 3 oxygens. And once again, right, the subscript goes to the guy to the left, right, of the formula. Any questions on any of those things? Now, I will tell you that sometimes people are taught, well, you know, just move like the charges down or the little subscripts, super subscripts up to get the charges correctly. Like, you know, move it this way and move it that way. And that works like 94% of the time. Yeah, so it won't work 100% of the time. So if you want 100%, just think about it as the balancing out to 0 and not just blindly swapping charges up and down. Otherwise, you'll be good. You know, like I said, about 94% of the time or so, you will get a lot wrong if you just kind of blindly switch, you know, kind of their positions, which sometimes people are taught just to blindly kind of move things up and down like that. All right, any questions on type 1 compounds here? Then let's talk about the other type of ionic compound here, which is type 2. And type 2 ionic compounds are also obviously metals and nonmetals. And again, we have our ions. And when that metal is involved, it is, again, the most important thing. Metal in this case is a type 2, which means it can have a variable positive charge. And again, that is your transition metals. And just to the right, as we talked about there, like tin and antimony and lead on the periodic table. So because the metals can have a variable type of charge, you actually have to, again, as I said earlier, tell people what the charge is in the name, and it's because it could be multiple ways. The good news is these are pretty much named the exact same way as type 1, except that you have to do that additional step. So here we're still going to take the whole name of the metal. We're still going to do the non-metal with the IDE ending. The additional thing that we have to put into this type of naming is a Roman numeral. And it's very common that people screw up on what the Roman numeral represents. The Roman numeral represents what the positive charge is on the metal. Like if you took one of those metal cations out, what the positive charge is on it. It is not what people commonly confuse it with, how many metals you have. So very commonly people think, oh, it's how many there is of them. It's not. It is the positive charge on one of the cations. So it's the positive charge on one cation. So for example, if we look at the one here, we have FeCl2. So the approach that you want to take on this is pretty much similar to the approach you do on anything, which is really identification first off. So what I mean by that is iron is a metal, Cl is a non-metal, which tells you it's ionic. We once again always look at the metal as being important, and that metal is dead center there in the transition metal region, which tells you it can have a variable charge. So that tells you it's type 2. The deal on this is an extra little bit of calculation in a sense. You need to figure out what the charge is on the metal. The good news is you will always know what the charge is on what it's hooked up to. So you'll always know really the negative charge guy. And when we look at it here, we have an iron, which I'm not really sure perhaps what it is, but I for sure know that Cl is group 7, which means it has a -1 charge, and there are 2 of them, which means there is a overall negative charge of -2 happening here. And because an ionic compound has to equal 0, and there's only one iron, the iron here has to carry, in this case, a +2 charge, right, to balance it out. And that is the thing that you have to kind of figure out. After you figure that out, you could roll into the name, and the name here would be iron, Roman numeral 2. Again, for the positive charge on the cation. And even though there are 2 of the Cl's, it has no effect on the name. This would still be chloride. So this would be iron Roman numeral 2 chloride. Again, the 2 for the +2 charge on the iron in this case. Question on up there. The reason we need to do this is if I had FeCl3, what would this be called? Well, if we take a look, right, we got 1 iron, and in this case, we have how many of the Cl's in this case? We have 3, which means 1, 2, and 3. That's a -3 charge, which means in this case, the iron needs to have a +3, right? And the name of this guy would be iron Roman numeral 3 for the charge. And once again, doesn't matter how many of those Cl minuses I have, it is still just going to be chloride at the end of it. Any questions on that there? So the additional thing that you have to do when a type 2 metal is involved is pretty much lay up a Roman numeral. Yeah, so you got to lay up a Roman numeral to indicate the charge on the metal. And again, you will always know the charge on whatever it's attached to. So you just kind of work your way backwards and figure out what will balance it out to 0 in terms of there. This, just like type 1, regardless of how many you have of either the metal or the non-metal, once again, no prefixes involved. So you should never find yourself Roman numeraling and prefixing at the same time. Otherwise, you probably could just put an X on it because it's going to be wrong. There's only a very small place where that could possibly happen. But in most cases, you should never have a Roman numeral and a prefix mixing together at all. So there is a place for the prefixes, which we'll talk about, where you should use them. This, again, is not the place. So anywhere where there's an ionic compound should not have a prefix. Any questions on any of that there? All right, so why don't you try this one here, PB. Okay, so let's take a look at it. Once again here, I would approach it the same way. I see lead, which is a metal. I see oxygen, which is a non-metal. So once again, that should tick the ionic box. When we get that ionic box and a metal's involved, that is the most important thing. When we look at the periodic table, we see lead is not a transition metal, but it is one of those ones to the right of it that's underneath the staircase where lead is SN, which is tin, bismuth, and that sort of area. They do have variable type of charges. So they do fall under a type 2 sort of metal. So that means we do need to figure out the charge on it. We do have only one of these leads, but we do have oxygen, which we know is group 6, and that has a -2 charge. And there are 2 of them. So that is a grand total of -4, which means in this case, lead actually needs to be +4. And this would be one of those ones where I was just talking about, if you just blindly move the 2 up there and over here, you get lead 2, which is incorrect in this case. So I would highly recommend you do not just blindly move things like that, which is a very common way people are taught. So as we could clearly see in this case, the name here should be lead Roman numeral 4 because of the charge. And once again, even though there are 2 oxygens, has no effect on the name here. So it's just going to be oxide in this case. Any questions on that? So as I mentioned, there are a number of places where you just blindly do that, you will get the wrong sort of charge. You actually get the wrong charge on the oxygen as well. You would get like a -1 on the oxygen, which is not the correct charge for that as well. Any questions on type 2? Now for type 2 naming, we are going to roll with Roman numerals always, and pretty much in all your chemistry classes, you'll roll with the Roman numerals. But there is sort of an older way that sometimes these sort of variable type charge metals are named, and they use sort of the historical sort of name. And it is, depending on the charge, it will either end in ic or us. The IC ending is for the one with the larger positive charge, and the OUS ending is the smaller positive charge. So if we look at iron 3 chloride, iron 3 chloride would be ferric oxide, which I think I have it there somewhere. And iron 2 would be ferrous chloride, which is what we see here, ferrous, which is based off of the sort of old school name of iron. So we're not going to use that older way of naming. Again, FeCl3 would be ferric chloride. We won't use it, but sometimes people will still use it for iron, and copper is very common. Like cuprous is sometimes used a lot in labs and stuff like that, or ferric or ferrous is used. So if you see those 2 endings, again, the one with the IC is the one that has a larger positive charge, and the one with the OUS is the smaller. Like you feel icky, you know, it has the larger positive charge, you know. So here's a table of that, and again, we will strictly roll with the Roman numerals in here and pretty much all your chemistry classes. But again, the iron is very commonly still kind of used very commonly by people, and copper as well. And as you can see, some of the other ones use more of their old school sort of names, like plumic or plumas for lead instead of lead. Mercury, by the way, is an interesting one. Let's just talk a second about mercury, and that sometimes confuses people. The mercury ions looks like this. And oddly, the one with all the 2s, a lot of 2s, is actually mercury 1, and the one with only 1 2 is mercury 2. So this is mercury 1 here. And this guy is actually mercury 2. And the reason for that is mercury 1 is actually a dimer of 2 mercury 1s together, which is why there's a 2 on the bottom. There's actually 2 mercuries, and they each have a +1 charge, gives you a +2 overall. So that's why it has all the 2s. And that 2 on the bottom is important because it will hang around when you see it in a formula. So for example, if I had Hg2O versus HgO in this case. In this case, I know that oxygen here is a -2, which means in this case, that is Hg with a +2, and that is Hg2 with a +2. So again, that extra 2 is still there on the bottom, as it is not here. So the top guy here with the Hg2O would be mercury 1 oxide. The guy on the bottom would be mercury 2 oxide. So the guy down here would be mercury 2 oxide. This guy here would be mercury 1 oxide. So again, that extra 2 will still be sort of present in the ionic formula when it comes together, And that's sort of an easy way to sort of figure out that it is actually the mercury 1 versus obviously the mercury 2, where that 2 will not be present there on the bottom. Question on that one there. All right, so as we talked about the rules for naming type 2, pretty much the only additional thing we're going to do is insert a Roman numeral to indicate the positive charge on our metal. Everything else is the same. Whole name for the metal, IDE for the non-metal. Again, positive guy, negative guy coming in that order. So why don't you try some of these here, and let me give you some names to write. Let's do iron 3 oxide. Let's do chromium 2 nitride. And let's do all right, so proper names on the left, proper formulas there on the right. Okay, let's take a look. Once again, we're going to start with identifying what we got going on. So cobalt's a metal, Cl is a non-metal. So once again, that is ionic. And again, when the metal's involved, that is the most important thing. So we see cobalt there also kind of in the center of the transition metal region. So that should tell you it is a type 2 sort of situation happening, which means we do need to figure out the charge. So once again here, I have 1 cobalt. I do know that Cl is -1 being in group 7, and there are 3 of them, which means that's a -3. So to balance that out, that's going to be a +3 in this case. And that's really all I need to figure out. So we're going to go with cobalt, Roman numeral 3. And once again here, chloride does no effect on the name in terms of how many we have going on there. Any questions on that one there? Coming to the middle, we got copper, metal, iodine, which is a non-metal. So again, ionic. Our copper being a transition metal tells us it's type 2, which means we want to again figure out what's going on. So we do have a copper, and we have 1 I, which is group 7, should have a -1 charge. So to simply balance that out, our copper here does need to have a +1 charge. So this would be copper Roman numeral 1, once again for the charge, and that obviously is the charge on that. And IDE at the end there, so copper 1 iodide. Any questions on that one? Coming to our bottom, that is tin, which is a metal. That is bromine, which is a non-metal. So again, ionic. Tin being just to the right of the transition metals, which means it is still going to be a type 2 way of naming. So looking at our tin, we have 1 of them. We have Br, which is group 7 -1, and there are 4 of them. So once again, that is the formula of each of those anions. And that means to balance it out there, we're going to have a +4 to our tin. And that would get us 10 Roman numeral 4, and then bromide here. And once again, the Roman numeral there. Any questions on any of those names? All right, so rolling to the other side, I see iron Roman numeral 3 oxide. So the Roman numeral actually again tells me the charge on the metal, so I don't have to figure it out. It actually told me that I am in this case dealing with iron with a +3. So that is what the charge Roman numeral means. Oxide is oxygen, which is group number 6. So our common number here is 6, and to get the oxygen to 6, you need 3 total there, and to get our iron that has a +3 charge, you need 2 of them. So once again, that is 2 irons, and 1, 2, 3 oxygens, and we will end up with our formula there, Fe2O3. Any questions on that one? Coming to our next one, which is chromium 2. So again, that means we have a chromium with a +2 charge. Nitride is nitrogen on the periodic table, which is group 5. It has a -3 charge. So once again, here's 6 going to be our common number. To get this guy to 6, we would need 2 total. And we would need, if you wanted to write them out, you can to help you. That's 3 of those chromiums. So that's going to give us 3 chromiums and 2 nitrogens in this case. Any questions on that one? And lastly here, nickel 4 means nickel with a +4. And bromide, which is bromine -1. To get us to 0, we will need a grand total again here of 4 of those guys, and that would give us NiBr4. Any questions on any of that? Now, clear, I'm writing out all the individual ions and stuff like that just to help you see it. So if it helps you to do it that way, do it that way. It don't really matter, right? You don't necessarily have to show, obviously, all the ions individually. You just need to give the right formula or the right name. Any questions on any of that? Okay. So this is type 2, which is ionic. Again, pretty similar to type 1, other than the additional step of adding the Roman numeral to indicate the positive charge on the metal. All right, so as we saw with our ionic compounds, metal most important. Anybody from group 1, 2, or 3 from the periodic table are zinc, cadmium, or silver. Do not need Roman numerals. Pretty much any other metal outside of that will need a Roman numeral because it can have a variable sort of positive charge. And again, that is where we use our Roman numerals. All right, so we got a couple more here just to finish out. So go for it there. Okay, so let's take a look. So here we have mercury, which is a metal, and oxygen, which is a non-metal. So again, tells us ionic. Our mercury being a transition metal tells us that we do need to figure out the charge. So once again here, we do know that that is oxygen. So this will carry a +2 charge. And once again here, we do not see the extra 2 on the bottom, right? So we do know that this is going to be actually mercury 1 in this case. So as we saw earlier, this would be our mercury 1 oxide. And again, we do need a Roman numeral here because it can have a variable charge based on the mercury. Any questions on that one there? I'm sorry, it's mercury 2. I mean, we get the right Roman numeral in there. Mercury 2 oxide would be much better there. So this will be mercury 2 oxide because of the charge, and there is no 2 on the bottom. All right. Next one here is magnesium, which is a metal, Br, which is a non-metal. So again, tells us ionic. It is magnesium. That's the most important thing here. It is group number 2 on the periodic table, which means it has a fixed positive charge, and it does fall under type 1, which means I do not need a Roman numeral. So this would be magnesium bromide. Here we look at Li, which is lithium, which is group 1, oxygen, which is a non-metal. So lithium, which is group 1, falls under type 1, so do not need a Roman numeral here. So that's going to be lithium and oxide. Lastly here, Cr is chromium, which is a transition metal. So that tells us it's type 2. We have fluorine, which is a non-metal. So in this case, we do need to figure out the charge. We know that fluorine is group 7, and there's 2 of them, which means that's a +2 charge. So that would be a little chromium, Roman numeral 2, and fluoride, IgE, at the end of it there. Any questions on any of those there? Yeah. Yeah, so Roman numerals are only for metals that basically have a variable charge, and that's pretty much going to be your transition metals. If you look on the periodic table, are just to the right below the staircase where you have things like lead and tin in that area. Those guys will have variable charges. Once again, the only 3 sort of transition metals that have a fixed charge is zinc, cadmium, and silver. So that's why they're considered more of a type 1 type of metal. Other questions? All right, we will